4 in gravity. I have 5 in gravity. That makes 6, I guess. One of them I don't know, though. So I wrote down the variable I'm trying to figure out. Give me a variable, Gavin.
Mass.
Mass was, did I say 10.0 kilograms? Did I give it 3 sig figs?
Yeah.
Okay, who's behind you? Gabe, give me another one. VI equals 2.2 meters per second. Ellie, give me another one.
UK equals 10, 0.10.
Kylie, can you give me the last one?
We're finding the distance.
We're finding the distance. I'm missing one variable I know. Anybody got it? Final velocity, VF, is going to be equal to what, Gavin? 0. Friction is involved. I'm kicking it. It's going to come to a stop. So I know all those things. So that's what you want to do first. The second thing you want to do is analyze the formula. So we start with W net, right? Because friction's involved. It's going to be equal to F net times the distance times the cosine of the angle. And that we know is equal to the change in KE. So I now have F net cosine theta times D is equal to 1/2 MVF squared minus 1/2 MVI squared. Then let's stop and think about these things for a minute. Both of these things represent kinetic energy. Final kinetic energy, initial kinetic energy. Are either one of those 0? Read your problem. Will either one of those end up being 0? What, Nick? The final velocity is 0, which makes my final KE 0. So I can get rid of this. Yes? So I really have 0 minus 1/2 MVI squared. So let's start plugging in some of the things we know. So what is my F net cosine theta D equals 0 minus 1/2 MVI squared. So let's figure out some pieces. Let's look at this. Let's look at our W net. We have F net. We have to take into consideration. When I have F net and I have a coefficient of friction involved, this is what you're going to do. You're going to use mu K times your force, which in our case here, our force has to be mg because that's all we're given in the problem, times my distance, times my cosine. What is my angle going to be here? If I'm moving this way, my friction is going this way, right? So my angle is always, when I'm dealing with friction, 180 degrees. So I have then equal to, I'm just going to say negative 1/2 MVI squared. Does that make sense? So then I'm going to plug in 0.10 times 10 kilograms times 9.81 times D times cosine of 180 degrees equals 1/2 10 kilograms times 2.2 meters per second squared. I almost ran out of room. So let's solve each side of the equation. 0.10 times solve them and see what you get. That is not right. So I got negative 9.81D here. But please plug it in and make sure you get that. And this is negative 1/2. Equals negative 24 joules. And this would be negative 9.81 kilograms times meters per second squared equals 8.4 joules. And this is D. And then I can solve for D. That's got to be about 2.4. Let's see. Yeah. Anytime I have friction involved, my cosine is 180, which gives me a negative value. You're going to see a negative value with friction, unless we're talking about total work. Then I would just add it on. And I think we probably should write that down. When Fk, or kinetic friction, is opposite displacement, the net work is negative. And that's because we're using cosine of 180 degrees. So that's how it works out mathematically. So there's three ways you might have to use friction. You may have to use it like we just did with the coefficient of friction that you're given and a mass and gravity. You may have to figure out what the friction is, what the work done by friction is, and add it to the work done by the force that's applied, if it's asking you for total work on the system. Or if it's asking you for what work is done by the machine, then you would have to subtract the friction. So you have to be really careful about the wording of the problem. Think, do I have to add this? Do I have to subtract it? What do I do with my coefficient of friction? If you have a coefficient of friction, 9 times out of 10, you're going to set it up just like this, which is why I wrote that one that way, so that you would see that. And I have a few on that paper for you to practice. But the last thing I want to show you today is power. And we can define power a couple of ways. Power can be called the rate at which work is done, but more specifically in physics we say it's the rate of energy transfer by any method. And there's all kinds of ways that we can use power and power to figure out different things. Like let's say you are on the stage crew for the musical and you have to lift the curtain or open the curtain in a certain amount of time. I don't want you to lift the curtain, I want you to open the curtain. And the curtain's pretty heavy on some stages. Ours is kind of heavy, but I've been on stages that are much, much heavier. So oftentimes there's a motor that does it for you. What do you have to figure out? You have to figure out how much does the curtain weigh? How far do I have to move it? How fast do I want to move it? Because there's like a very narrow line. I've seen this happen. If your motor is too strong, the curtain will come off the rod, and that's a giant mess and lots more work. So you don't want that to happen. So sometimes you have to do some math to figure out, yeah, have you seen ones that open really slow before? Yeah. You have to do some math to figure out, hey, what's the best thing? What's the unit for power? Does anybody know? Watts, good. The unit
I think it's W.
for power, you're thinking W, would be, well, it's work divided by time, the rate of energy transfer. So this is work over time, work per unit of time. So joules per second, 1 joule per second is equal to 1 watt. And watt is a fairly small measurement. That's how we buy our light bulbs. Like you can buy a 40-watt light bulb, that's pretty dim. You can buy, if you go to Lowe's and really check them out, a 500-watt light bulb. That is pretty bright. Those little Christmas lights that are on your tree, individually those only put off like about 0.7 watts. If you have those lights outside that like shine on your house, like look at my house lights, I don't really know what those are called, but anyhow, those are only about 7 watts actually. So there's a wide range of those things. You have to remember that 1,000 watts is 1 kilowatt, because sometimes you're asked for an answer in kilowatts. If you read your parents, like the power bill your mom and dad get, the AES bill, I don't know if you all have AES or Pioneer or whatever, it's given to you in kilowatts. You're billed in kilowatts usually. So really, honestly, there's 2 formulas you might have to use for power. P equals WT, which remember that could be FD over T, it could be mg over T, it could be FD cosine theta over T. Got to remember all the variations. Or sometimes power can simply be set equal to the force applied times the velocity at which the object is moving. So this might be mgv. And you have a problem on that handout where you'll actually have to use that one. So we're looking at work per time interval. Oh, here's a good question for you. What do we measure power in the United States? Do you know? No, not really. Horsepower, good. You know where that harkens back to like the old years, like 200 years ago when they settled the United States. How did they farm? With horses.
But isn't like 1 horse like 3 horsepower?
1 horsepower equals 7, yeah, about, of those big Belgian workhorses.
Oh.
What they can pull, yeah. I gotta think about this. 1 horsepower is equal to 746 watts. So if you ever have been on a really like good motorboat, the boat motor's on the back, even if you're on a little fishing boat, if you read it, it'll tell you how many horsepowers it is. If you use this, next time you're out and impress people, you can tell them how many watts the motor's putting out. Okay, so let me give you a problem to try. You'll have to write this one down. I don't think I typed it. Let's say we'll go back and talk about the musical curtain. Let's say we have a 193 kilogram curtain, and I want needs to be moved. Usually they're around 200 kilograms. Let's say, I'm trying to think here when it opens. Let's say it needs to be moved 7.5 meters in, what's a reasonable time to open the curtain? In 5 seconds. You have, I'll give you 3 choices, 3 motors. Pick one. We'll have a 1 kilowatt, let's see, 3.5 kilowatt, and a 5.5 kilowatt. Now I want you to get together with your lab partner, and I want you to decide which motor you're going to use. Which one's going to work the best. So go ahead and get up and move, figure it out. When you're done, sit down and we'll talk about it. See if you can figure it out. If you can't, call me over and I'll help you.
FNet always equal MK M times gravity?
If you are not just have a force spelled out, yes. If you're trying to move something, it's its mass times gravity. That gives you the force. Anybody feel like they don't even know where to start? Okay, good answer. Is it a big number? So remember, that's what? Watts. So what do you... Yes. Anybody need help? When you get it figured out, I would pull out my formula card and put the last couple formulas on there. That way when you're studying to learn your formulas, you've got them all together. When you've got your best choice, come back. Okay, so if I wanted to burn the motor up and not open the curtain at all, JC, which one would you pick? A, that's what I would pick too. If I wanted to smother the members of the cast by having the curtain fall on them, which one would I pick, Kylie? C, yes. What's the best motor, Kira? B, what'd you guys actually get for an answer? 2.8, yep, good, okay. So that's an example of how we could use power, or why we might have to use power. Now, I had that paper. Okay, now pull out the paper that I gave you today. We've already done the one on the front page. I want you to do number 1, where you're really going to have to think about your formulas. Let's see. And I want you to do number 2, but I do want to point out, because we are moving up a driveway with a slope, that you're going to have to use sine instead of cosine. So make yourself a note of that, because you're really doing vertical motion, not horizontal. And then let's do number 3, B through E. B through E. And then under the power portion, let's do 1, 2, and 3. No, 1, 2, and 4, sorry. 3's a nightmare. And in number 4, I want you to tell me how many years it's going to take. I didn't type that on there, but that's what I want to know once I figured out the answer. It's like, that's way too long. So tell me how many years is it going to take for that to happen. Okay? Now, I want you to start, try to get one of them done, and then I'll give you some time tomorrow. I've got one little thing to talk about tomorrow, a few more problems, and then you'll have all period to work. Tomorrow's Wednesday already. I keep forgetting it's not Monday. Right? Isn't tomorrow Wednesday? Wednesday and Thursday I'll have the review ready for you. Friday we're going to take the first part. Monday we'll take the second part. Do you have a preference as to problems or multiple choice short answer first? You just let me pick. No. Who said something? Did you say something, Bianca? Problems? Okay, we'll do problems first. I don't care. I just want to know what to make up first. Okay, so you've got 7 minutes. Try to get at least the first problem done. Luke, I forgot to record until we had already started class, so I'm going to scan the first few pages of notes, and they'll be on Classroom also.